Today, we're going to work our core, so get ready to sweat. Oops, sorry, wrong core. Hey, we've traveled far and wide, down to the Earth's inner core and up into outer space. But what if we could combine these adventures and find out what hides in the innards of other planets and moons in the solar system? With the help of this interstellar hyperdrill, we can achieve that, at least in part. Coordinates are in, all systems ready, and our first destination is the Moon. Our moon, in fact. We land on its gray and desolate surface under the black sky. No blue here because there's very little atmosphere to disperse the light. The drill starts working, and we first go through the outer layer of the moon, the crust, just like on Earth. We're on the sunny side, so the thickness of this layer is only 43 miles. But were we to land on the dark side, it would be more than twice as thick. The moon is a rocky body, so its crust is largely made of silicon, iron, aluminum, calcium, oxygen, and magnesium, with much smaller amounts of other elements. Further down, we find the mantle, and it's a long and tedious journey through. This layer is about 850 miles thick. It gets hotter as we go deeper, finding composite minerals, pyroxene and olivine. They're made of iron, silicon, oxygen, and magnesium in different proportions. Finally, we break through the hard layers and into the semi-molten outer core. Another journey of about 93 miles ahead through this scalding swamp, and we dive into the iron ocean of the liquid core shell. It's nearly 60 miles thick, and the molten metal threatens to evaporate us. But this drill was made to sustain an extremely heavy onslaught. And that's how we finally come to a sudden halt. In the deepest reaches of the moon, there's a solid iron core, which is 150 miles thick. We could drill through it, but it would be unnecessary. So we just set the flag here and skip to the next planet on our drilling list. And it's Mercury. It was hot deep inside the moon, but on the surface of the smallest planet in the system, it's even hotter. That's because it's so close to the sun, of course. Alright, let's drill. Mercury has a pretty thick outer shell, which is both crust and mantle, going about 250 miles deep. Not the most fascinating journey, it's not unlike the Earth in many respects. But then, the drill stops, ramming into a solid metal wall. It's Mercury's core, which has a diameter of over 2,500 miles. It takes up to 85% of the planet's overall diameter. No use trying to drill through this one. It's fully metal and extremely dense. Skipping to the next planet, and we're on Mars now. Oh look, it's sunset here, and the sun is making the sky hazy blue. But you know the drill. I mean, we're here to drill, so that's what we do. Mars's crust is quite thin compared to Earth's, just 6 to 30 miles deep. Its composition is much the same though: iron, aluminum, calcium, potassium, and magnesium. That's one of the reasons why humans are looking to colonize the red planet one day. It's very similar to our own. We're very quick to drill through the first layer, and the second one, the mantle, is now upon us. It's a hard and rocky layer about 1,100 miles thick. Thanks to its size, Mars isn't seismically active any longer. There's simply no magma boiling close underneath the surface of the planet, making it silent and docile. It's a long dig, but we finally come to a screeching halt, bumping into the core. A ball of iron, nickel, and sulfur with a diameter of 2,000 to 2,600 miles. This core is bigger than that of Mercury, but the planet itself is larger too, so it figures. Okay then, our next stop is even more interesting, because it's Jupiter. This gas giant has a mass twice that of all the other planets in the solar system combined. And we landed right in the middle of an ocean. The ocean, I dare say, it's the largest one in the whole system, and it's made of liquid hydrogen. The drill goes smoothly through the surface of the planet because there's no rock or hard metal here, only gas and liquid. But the shaking, yikes! The pressure on this planet is more than just huge, it's unimaginable. The drill is barely able to withstand it, and as it's going deeper, the pressure's becoming higher too. We've reached Jupiter's core, and it's nearly too much to bear. The temperature here is about 90,000 degrees Fahrenheit, and the core itself is not solid but liquid as well, kept together by the immense pressure from all sides. The drill starts to rattle. Bad sign. Let's get out of here before it breaks. Whew! No winds, no pressure, no heat. All around us is a vast icy wasteland, crisscrossed by ridges and reddish bands. It's Europa, one of Jupiter's most promising moons. As we drill through the ice, let me explain. Europa is one of the candidates to have extraterrestrial life in the solar system, and it can be found right beneath the icy shell through which we're now digging. It's only 10 to 15 miles thick, while down below is an enormous saltwater ocean, twice bigger than all of Earth's oceans combined. The deepest point on Earth is Challenger Deep, and it's a bit over 6 miles down. The ocean on Europa, on the other hand, can be up to 100 miles deep. Who knows what can be lurking in that deep, dark sea? Anyway, we travel fast through the water and finally reach the bottom of the ocean. The mantle starts here, and it's made of rock, just like on Earth. And not much deeper in, we find the metal core of the moon. Europa is a little smaller than Earth's moon, so it's no surprise we reach its center pretty fast. Okay, skip drive on. Let's go further. Oh, I'd rather we drill in as fast as we can. Just look around, it's blazing here. We're definitely on Io, another moon of Jupiter, and the most volcanically active world in the solar system. Look, that volcano is twice the size of Everest, and it's erupting right now. Thankfully, we're under Io's surface already, but that's not to say we're safe. It's all molten down here too, mostly yellow and brownish hue, due to the huge amounts of sulfur. The stench must be horrible. Anyway, the most peculiar feature is that both inside and outside, everything's always on the move on Io. Jupiter and its other moons create tremendous tidal forces, making the surface of Io swell over 300 feet up and down. Like the largest tsunamis on Earth, only here it's not water but rock. The deeper we go, the calmer it gets though, until we're finally at the iron core. It's still hot here, but at least there's no shaking and swelling like above. Let's put up another flag and go to the next point. And that would be Saturn, the second largest planet of the solar system and the one best known for its spectacular rings. Not the only one to have them at all, mind you, but we'll get to it. Now, as you've surely noticed, our drill is simply falling down through the gaseous hydrogen and helium, making up most of the planet's surface and atmosphere. No need to work here. Just wait and hope the immense pressure won't crush our drill to a hunk of junk. At last, the pressures become so enormous that we find ourselves in the liquid hydrogen, and here we start diving. Soon we'll reach the solid core of Saturn. Ah, here we are. It's made of iron and nickel and is actually quite small compared to the rest of the planet. Well, the last destination awaits, so come on. And here we come, Neptune. The drill immediately deploys anchors because the winds here are extremely powerful. They reach speeds 5 times greater than the most devastating hurricanes on Earth. Neptune is covered in a pretty thin layer of hydrogen and helium, just like Saturn or Jupiter. But underneath, there's much more than that. It's hot, windy, and lonely here on the outskirts of the solar system. So let's dig already. Beneath the gases, there's suddenly a bubbling hot mass of water, methane, and ammonia. Phew! These substances are hot, despite Neptune being called an ice giant. The name comes from its core. Deep inside, where we're quickly headed right now, a small ball of rock and ice sits all alone. And despite the boiling temperatures above, the ice beneath is ever cold.
As soon as the Earth is cut in half, almost all living creatures will come to an end. An apocalypse will begin, which has not been shown in movies. The atmosphere is damaged, the magnetic field will change, and the planet's landscape completely alters. But the planet will be completely renewed, and life, like a phoenix, will be reborn from the ashes. A super powerful laser would be needed to separate the planet. Such a laser has to receive energy directly from the sun. The weapon goes into space on a rocket, thousands of miles above our world. Then, once the laser arrives at its destination, it opens wide to expose plates of solar panels. The laser absorbs and concentrates the sun's rays. Then a powerful energy beam with the diameter of several cities shoots into the middle of the planet. Oceans through which the beam passes boil and evaporate from the high temperature. These vapors turn into a vast thundercloud in the sky. A strong wind drives these clouds over the continents. Heavy rain falls, which floods not only cities, but entire countries. As the tectonic plates shift, tsunamis are created. Huge waves crash onto the shore. The Earth is split in two. And this is just the beginning. The structure of the Earth, or rather, each half of it, is changing. Strong earthquakes occur all over the world. The worst disasters happen near the fault line. Billions of tons of ground are smashed. Massive landslides drag entire cities below. Chunks of land, thousands of miles in size, shoot away from our planet. All living creatures on these pieces of land fly into outer space. Other broken pieces of the planet land on the half that is closest to them. Imagine a huge rock the size of a whole city falling from the sky, and there will be hundreds or thousands of such stones. Those who live far from the cut site have a chance to survive, but even there, earthquakes will destroy houses. The moon will also start to throw off pieces from itself. These pieces, like a meteor shower, will fall onto the Earth halves and create massive explosions. These explosions will create fires. The skies will be covered with ash, and until it settles, we won't be able to see the sun. Both parts of the planet are drifting away from each other. The red-hot heart of our Earth is right in the center between the two. This is the Earth's core, consisting of molten metals. Each half of the core exudes energy comparable to a star. Between the two parts of the planet, a layer of such hot space is created that nothing can survive there. Any item that falls into this space immediately turns into ashes. The mass of the core is much larger than the ground mass, so there's a higher level of gravity. The core sucks in everything that comes close. You can't travel from one part of the Earth to the other. The core's gravity attracts any shuttle. Each half of the Earth now lives on its own. Typically, the core inside our planet rotates and creates the Earth's magnetic field. This field is a shield that protects us from the sun and space. If the shield is damaged, solar and cosmic radiation passes through the atmosphere. Because the core is divided into two parts, the Earth's magnetic field becomes unstable. Power outages begin in both parts of the planet. Microwaves, TVs, kettles, traffic lights, computers, everything is broken. The screen of your laptop or phone starts turning on and off. The video may freeze and the battery runs out and charges in 1 second. Satellites stop working, which means there will be no more GPS. High-frequency radio waves used for communication stop working, which means you can't make calls and send texts. In fact, all power plants may sink underground or be flooded because of the earthquakes, so there might not be electricity at all. Some people are sensitive to solar storms and experience severe headaches. When the magnetic field is damaged, the surviving people and animals will suffer from severe migraines. Scientists will have to invent special helmets to protect people from the sun. For full protection, people will have to live in underground cities. Compass needles no longer point north. They just spin in different directions. The birds go mad. They don't know where to fly to wait out the winter because the south no longer exists for them. All animals stop migrating. In the sky, planes can't navigate. Plants and flowers can't grow naturally thanks to the increased radiation from the sun. Livestock are poorly fed. The quality of products deteriorates. There's famine. The main goal for people on each half of the planet is survival. In some places, closer to the fault, the Earth's atmosphere is completely damaged. The conditions there will be similar to those in space. There is no air or heat. Only in a spacesuit can you stay in this territory. Unfortunately, you won't be able to jump and fly because gravity still works. Besides, it's gravity that becomes the salvation of our planet. Both parts of the Earth won't fly away from each other because of the force of gravity. Instead, they will rotate and start to attract each other. In 100,000 years, both parts of the planet will reconnect once more, and the Earth will be completely renewed. Since the core is molten metal, it will return to a single heart, but it will take much longer to connect the solid rock of the halves. A scar forms along the entire fault. The scar will be overgrown with forests and flooded with oceans, but there will be strong earthquakes in some places near this scar. By this time, all living things have probably disappeared. On our planet, conditions are about the same as 4.5 billion years ago. Seas and oceans boil, lightning strikes everywhere, tectonic plates change their shape, and lava flows from volcanoes in a rapid stream. The Earth looks like a vast boiling pot, inside which life is gradually created. Because the Earth has decreased in size and the core hasn't changed much, the gravity will be different. On land, it will be more difficult for an ordinary person to walk. They will weigh much more. In such conditions, new, previously unknown life will be created. Today, the world's atmosphere and oceans are polluted, the population is increasing, and glaciers are melting. In the future, things could be much worse for our planet. In 1,000 years, when humanity has mastered space travel, we may decide to change our residence. We'll start looking for other Earth-like planets, and maybe we'll find something. However, nothing compares to our first home, and humanity decides to cure it. Perhaps we'll come up with the idea to divide the planet in half and live on one side. And after 100,000 years, we can come back to a new healthy home. What if you divide other planets? Since they don't have a magnetic field, they won't be as affected. For example, Venus and Mars have no seas, oceans, or lakes. Some scientists think they're entirely dried up because the magnetic field has disappeared there. This led to the complete destruction of the atmospheres of these planets. The solar wind blew across their surface with such force that it dried up all the liquid. The Earth's atmosphere reflects this wind, so thankfully, we're safe. There would be no significant cataclysms on other planets, except for earthquakes. Like Earth, the two parts of each world would simply rotate until they reconnect once more.
Well, looky here. You're about to figure out what lies under the surface of each planet in the solar system. Get into your spaceship, equipped with the largest drill you can only imagine, and off you go. You start with Mercury. It's the closest planet to the Sun. At first sight, the place looks similar to our good old Moon. But after landing, you understand it's an illusion. All around your spaceship, there are craters left by meteorites. The planet's surface is littered with huge steep hills. Some of them are 2 miles high and stretch for hundreds of miles. You start drilling and immediately understand it's going to be tough. Mercury is the second densest planet in the solar system, topped only by Earth. The planet's outer shell is 250 miles of solid crust and rocky mantle. After getting through it, you see Mercury's metallic core. It takes up almost 85% of the planet's volume and contains more iron than any other planet we know about. You don't need to drill anymore, the outer core is liquid. But once you reach the solid inner core, you have to switch that drill on again. The next planet you're going to explore is Venus. It's the hottest planet in the solar system. The average temperatures there are high enough to melt lead. The pressure on the planet is 90 times greater than that on Earth. Your spacecraft is traveling through thick clouds of sulfuric acid. Venus's surface is reddish-brown and extremely dry. You land in the middle of a flat, smooth plain. Plains like this cover 2/3 of the planet's surface. Well, you get down to work. The drill starts moving through the crust. It consists mostly of basalt and is almost 12 miles wide. The next layer is a molten rocky mantle. After some time, you get the feeling it'll never end. No wonder, it's 1,200 miles thick. Finally, you arrive at the planet's metallic iron core. It's huge, twice wider than the mantle. See that blue sphere slightly to the left? It's Earth! How about you skip it for the moment and get back to it later? Right now, Mars sounds so much more exciting. Whew! The place is freezing cold. The temperature is minus 80 degrees Fahrenheit. The planet looks reddish, and as soon as you make your first step on its surface, it becomes clear why. The ground's covered with rusty-colored dust. Its fine particles are also floating in the air around you. In most places, that dust layer is 7 feet thick. You start drilling through the planet's thin crust. It's made up of volcanic basalt rock. Pretty soon, you reach the mantle. It's composed of oxygen, silicates, and other minerals, something like a soft, rocky toothpaste. The red planet's mantle is much thinner than Earth's. It's 1,100 miles thick at most. You feel that the drill begins to move a bit differently. Must be the core. It's made mostly of iron, nickel, and sulfur and is between 900 and 1,200 miles across. And unlike Earth's core, it doesn't move. Time to visit the largest planet of the solar system, Jupiter. Almost 1,300 Earths could fit into this huge thing. It's also alarmingly high, about 43,000 degrees at the core. But you can't land on Jupiter because it doesn't have any solid surface. The planet is a gas giant, the key word here being gas. Your drill is also of no use, at least at first. While descending, you watch thick brown, yellow, red, and white clouds passing by. Thanks to them, the planet looks colorful and beautifully striped. You keep going deeper toward the center of the planet. Its atmosphere is made up of hydrogen and helium gas. Soon, you see the hydrogen become liquid under immense atmospheric pressure. And closer to the core, this liquid turns into a mixture of metallic hydrogen and helium. You reach something that looks like a core, but even with the help of your equipment, you can't figure out whether it's a molten ball of liquid or a solid rock 14 to 18 times the mass of Earth. Maybe, one day, astronomers will help you answer this question. The next planet turns out to be exceptionally windy, like me. The winds on Saturn travel at more than 1,100 miles per hour at the equator. From above, it looks as if the gas giant has a solid yellowish-brown surface. You get through several different layers of clouds, and suddenly, you realize you can't land your spacecraft here as well. Saturn is the least dense planet in the solar system. It has only 1/8 the average Earth's density. If you found a pool of water large enough to fit the ring planet, the gas giant would float. If you kept going down, you'd probably have found Saturn's core. It's likely to be rocky, with hydrogen and helium surrounding it. You're approaching the ice giant Uranus, which means there's going to be some surface to land on. Or not. The planet isn't solid. You fly through the upper atmosphere and sink into the liquid icy center. The ice, which makes up 80% of the planet's mass, is actually a hot, dense fluid. It consists of water, ammonia ice, and methane. This part of the planet is sometimes called a water-ammonia ocean. This ice surrounds a solid rocky core. That's where you can finally use your drill. The core's small, half the Earth's mass. Compared to other planets, it's also rather cool, a mere 9,000 degrees. You're reaching the farthest point of your journey, Neptune. It's 4 times the size of Earth, but 17 times as heavy. The bluish surface you see when coming closer is a layer of permanent clouds and swirling gas. Below this surface, there's a large mantle, liquid and red hot. The mantle is rich in methane, ammonia, and water, and equals 15 Earth's masses. At last, you have something to drill. The planet's core is solid. It consists mostly of iron and other metals. Keep drilling until you're at a depth of 4,500 miles. Astronomers are almost sure that's where you'll find a diamond layer. That's right, it rains diamond crystals there. Well, time to go back home. People have drilled pretty deep holes here, but they were never deep enough to even get through the crust. After the drills traveled 1/3 of the way, the temperature reached 360 degrees, and the equipment couldn't operate any longer. But your drill is much stronger than that. That's why you easily move through the crust. It takes up only 1% of Earth's volume and is broken into tectonic plates. They let heat escape from the Earth's interior. You reach the mantle. This layer is about 1,800 miles thick and makes nearly 84% of the planet's volume. It consists of silicate rocks rich in iron and magnesium. Well, you don't need to drill anymore. The 1,500-mile thick outer core is liquid. It consists of iron and nickel, but the pressure isn't high enough for it to be solid. You pass through the boundary between the outer and inner core. It's quite a challenge. The temperature there is 10,800 degrees, as hot as on the sun's surface, and the pressure is 3.3 million times the atmospheric pressure at sea level. The inner core is a solid ball made of iron and nickel. Its radius is 760 miles. It makes 20% of the Earth's radius and 80% of the Moon's. Scientists know what's going on under the crust of the planets that are millions and billions of miles away from us. And they don't even need to go there, drill through their surface and peek inside. They combine information about the planet's density, magnetic field, mountain ranges, heat, and seismic activity to make their smart assumptions. For example, Earth's magnetic field shields us and the atmosphere from solar flares and solar winds. Scientists believe that it exists thanks to a hot iron core inside the planet. It rotates and generates invisible protection, like an enormous scorching hot dynamo. And this magnetic field is way stronger than that on Mars. It probably means that something happened to the red planet's core. Maybe it cooled down and kinda switched off. Or maybe there wasn't any magnetic field to begin with. There are loads of active volcanoes on Earth's surface. That's how scientists can conclude there must be a relatively thin crust, and the mantle must be made of liquid magma. But Martian volcanoes aren't active anymore. There could have been a hot liquid mantle under the planet's crust once, but after the volcanoes formed, something went wrong. The interior probably cooled down, or the crust somehow became thicker. Whatever it was, it successfully stopped magma from getting to the surface. And then there's also seismic activity. If many Earth or Mars or Venus quakes happen on the planet, there's a lot going on under the surface. If we talk about Earth, it's the movements of tectonic plates. Most earthquakes happen along their edges. If there's little seismic activity on the planet, it might have no plate tectonics. Then its interior is calm. Researchers also pay attention to how long it takes a seismic wave to go through a planet or how it echoes inside. It can help to get more information about the density of the crust, what the mantle's made of, and so on. But scientists have to be extremely careful with the causes of these earthquakes. Sometimes they can occur after meteorites hit the planet, and it has no connection with the processes going on under the surface. Of course, these last two methods will only work with rock planets, mainly because gas giants have neither volcanoes nor seismic activity. Boy, all this talk about thin crust and thick crust is making me hungry. Hey, you up for some pizza? Not so long ago, astronomers discovered a planet that got the name of UCF 1.01. This world is about 33 light-years away from Earth. This makes the planet our next-door neighbor, in the cosmic scheme of things, of course. Honestly speaking, the space body is only a planet candidate because astronomers haven't measured its mass yet, but they have high hopes. The wannabe planet is very different from our Earth. Just 1.7 million miles away from its star, it completes its orbit in a day and a half. It's a scorching, deserted world with the temperatures at the surface rising up to 1,000 degrees. Even more astounding, the entire planet is likely to be covered in magma. Even if UCF 10 ever had an atmosphere, it has definitely boiled away by now. But then, the question is, what if Earth once went through some catastrophic event and it left our planet in the same state, boiling hot with the surface covered by a thick layer of lava? Would people manage to adapt to such conditions and move to live underground? It sounds unbelievable, but experts are sure that with time, humans would turn into healthy and rather happy mole people. Of course, life would be very different than today. No more sunsets and sunrises. No more traveling by plane and space exploration, unless people found a way to launch a rocket from under the ground. No more picnics in the park or sunbathing at the seashore. People would have to build a vast network of underground tunnels that would connect major cities. The most likely transport in this new world would be silent high-speed trains and electric cars. After moving underground, people would have not only physical but also psychological difficulties. In the beginning, their new home would be a dark, barren place, without fresh air and devoid of any color. To adapt to these tough living conditions, people would have to make some design changes. Greenhouses, well-lit parks with trees and illusions of the sky, familiar scents and sounds. All this would help people to adjust to their new life. After living underground for several generations, people would start to look a bit different. Pale because of the lack of sunlight, with sensitive large eyes adapted to dimmer lighting and more developed lungs. As for the very possibility of living underground, well, hear me out. You might imagine the Earth's depths as a huge mass of compressed solid rock. But the reality is different. This mass is heavily cracked. Water runs down the fractures and cracks in the planet's outer layer, the crust. Some of these streams reach the depth of many miles. In other words, subsurface Earth could probably support plant and animal life. If people lived underground, they wouldn't have a shortage of fresh water. Its reservoirs in the planet's interior contain 100 times more water than all the lakes, rivers, and swamps combined. Plus, this water trickles through the soil that acts as a purifier. But people would have to be super careful to keep the sources of water intact. Otherwise, the underground cities would get flooded and turn into giant water-filled traps. It would also be a great challenge to live without sunlight. Plants can't survive without the sun's ultraviolet light. It's absolutely necessary for photosynthesis because sunlight is used to get nutrients from carbon dioxide in water. One of the byproducts of this process is oxygen, the thing people can't live without. So, no sunlight equals no plants equals no oxygen. Sunlight is also crucial for humans. For example, it helps your brain release serotonin, a hormone that boosts your mood and makes you feel focused and calm. Thanks to the ultraviolet B radiation in the sun's rays, your skin produces vitamin D. It's vital for a strong immune system and healthy bones, teeth, and muscles. That's why people would have to find a replacement for sunlight. Luckily, LED lamps that can give off UV wavelength could produce the light human bodies and plants crave so much. In the new underground world, there wouldn't be large sunlit fields. Instead, there would be sprawling greenhouses with LED lights shining from the ceiling. Special machines would feed plants and crops with recycled water rich in nutrients. In some areas, located in the narrow underground faults, people would use something like shipping containers instead of greenhouses. These containers would be packed with vertical rows of plants and blue and red LED bulbs. As for people, they would have to follow a vitamin D-rich diet. It'd mean eating a lot of egg yolks, cheese, fish, spinach, soybeans, and so on. If these foods weren't enough, vitamin D supplements would do the trick. Without daylight, people would have problems with their circadian rhythms that regulate sleep patterns. If you were isolated somewhere without a glimmer of light, you would easily sleep for 48 hours at a stretch. That's why people living under the Earth's surface would rely on artificial lights to control their internal clock. There wouldn't be any problems with electricity. It would be produced with the help of the Earth's inner heat. Such kind of energy is called geothermal, from the Greek words geo, earth, and therm, heat. It can be extracted from hot water and rocks. Like an onion, our planet is made up of several layers. The innermost part is a solid core around 1,500 miles across. Made of iron, it's surrounded by a scorching outer core. It's up to 1,400 miles thick and is mostly composed of liquid nickel and iron. The next layer is the mantle. Even though lots of people picture it as lava, the mantle is actually rock. But this rock is so hot that it flows, just like road tar. The temperature in the Earth's core is as high as 10,800 degrees Fahrenheit. That's almost 1,000 degrees more than at the sun's surface. The mantle is also blistering, from 7,000 degrees at the boundary with the core to 400 degrees in its outer parts. No wonder people wouldn't have any difficulties with transforming all this heat into electrical energy. But because the insides of our planet are insanely hot, people wouldn't be able to build cities too deep underground. All inhabitable areas would most likely stay closer to the surface. The Earth's outermost part, the crust, is like the shell of a hard-boiled egg. It's broken into gigantic blocks called tectonic plates. When two plates collide, mountains get formed and new rifts appear in the seafloor. They have different width, from 25 miles thick beneath the continents to 5 miles thick beneath the oceans. These blocks travel around, floating on the Earth's mantle, slowly, almost imperceptibly. It means underground cities would also move, but it would be next to impossible to notice these movements. Oh, by the way, people started to believe there might be another world inside our planet in the 17th century. The idea got the name of the hollow Earth theory. It claimed that half the planet was taken up by its surface weight. Below the surface, there was some empty space. A small sun hung at the very center of that cavity, creating a comfortable tropical environment on the inner side of Earth's surface. One could enter the Earth's interior through one of the openings near the south and north poles. A race of advanced humans was believed to live inside the planet. They were peaceful and lived for centuries. Well, obviously not humans. They had unique technologies, for example, flying vehicles. And since the climate inside the planet was better than that on the surface, this race was much stronger and healthier. Even though this idea sounds like science fiction, several famous scientists supported it. Some people are still sure there's another world inside our planet. But if the Earth was hollow, it wouldn't have a magnetic field. And without a magnetic field, solar winds would rid our planet of its atmosphere in the blink of an eye. This would leave our green planet deserted and uninhabitable, like Mars is. The magnetic field on our planet exists thanks to the processes going on in its very much not hollow center. Liquid metals are constantly moving in the Earth's outer core, generating electric currents. When the planet rotates around its axis, the electric currents form a powerful magnetic field. The sunward side of the magnetosphere is as large as 10 Earth's radii, and the other side stretches out in a magnetotail that spreads for 200 times the Earth's radius. Okay, I officially give up on the hope that the moon is made of cheese after all. Wow, not even Gouda. The shiny lunar ball, or a curved banana, or half of a coin, depending on what phase it's in, has different layers inside, just like Earth. One of these layers is called the inner core. About 20 years ago, scientists were observing how the moon rotates. Using that data, they concluded that it had a fluid outer core. But the inner core was hard to study, so they didn't know if it was solid like a rock or molten like a hot liquid. But things are clearer now. Astronomers have collected data from different missions, including the Apollo missions, where astronauts went to the moon and gathered information themselves. Plus, they've used a special technique called seismic data. This method is all about studying how sound waves move through things. Take earthquakes on our planet as an example. When an earthquake happens, it creates waves that travel through the ground. Scientists can detect and analyze these waves to learn more about Earth's interior. The same idea can apply to other objects in our solar system, or planets, or, in this case, the moon. When quakes or moonquakes happen, they generate sound waves, and by carefully listening to and studying these waves, scientists can create a detailed map of what's inside the object. They can figure out things like different layers, what they're made of, and how they're arranged. To check the moon's deep interior, scientists also use something called laser ranging. This method measures the distance between the surface of the Earth and the moon very precisely. And ta-da! Our natural satellite's inner core is a dense, solid ball made of iron, just like Earth's. It's about 310 miles wide, which is nearly 15% the size of the entire moon. Researchers also have stumbled upon evidence that supports the theory that the layer between the moon's surface and its core, called the mantle, has been moving around as the moon evolved over time. This movement is something we call lunar mantle overturn, and it could explain why we find elements rich in iron on the lunar surface. Mantle material ends up being carried upward, and the volcanic rock remains in the moon's crust. Some of the materials in this rock were too dense, like me, so they just sank back through the lighter crust material all the way to the core mantle boundary. It's like a cycle where the moon's mantle material goes up during volcanic activity, carries iron-rich elements to the surface, and then sinks back down. There's another mystery scientists have been trying to solve: what caused the moon's magnetic field to weaken and nearly disappear over time? It seems that now that we know about the iron core and the global mantle overturn, we might get some more answers about the moon's magnetic field. Knowing what the inner core is like can help us better understand the moon's history as well as the history of our entire solar system. Now, one of the theories that's widely accepted about the origin of the moon says there was a massive collision between Earth, in its early stages, and another mysterious object in our solar system. It's called the Large Impact Theory, and this collision was so strong it ripped off a big chunk of the primitive molten Earth. I mean, not so big compared to what's left. If you put a US nickel next to a green pea, you get a good idea of how big our planet is compared to the moon. Now, this chunk was set into orbit around our planet, and this might have happened about 95 million years after our solar system formed. The object that collided with Earth could have been about 10% the mass of our home planet and roughly the size of Mars. Well, it makes sense. Earth and the Moon do have similar compositions after all. Of course, there are other ideas about how the Moon formed. One says that the gravitational force of our planet captured it. This means that the Moon was just an object innocently passing by when suddenly it got attracted and pulled into Earth's orbit. There's even a hypothesis that Earth stole the Moon from Venus. Ooh. In that case, the Moon shouldn't complain. I guess the view is way better here. So yeah, the Moon and Earth are similar when it comes to rocks and some minerals. But the Moon doesn't have the same atmosphere as our planet. Its atmosphere is thin and consists of some weird gases that include potassium and sodium, which is not something you can find in the atmosphere of Mars, Venus, or Earth. And the rocks on the Moon don't contain water. But that doesn't mean there's no water at all up there. A long time ago, in the 17th century, astronomers saw large dark spots on the Moon's surface. One of these astronomers thought these spots looked like oceans, and he called them maria, which means seas in Latin. Other astronomers also made maps of the Moon, and they used the term maria to describe these dark spots. For example, Mare Tranquillitatis translates to Sea of Tranquility, where Apollo 11 made its touchdown. But it seems those dark spots are not actually oceans. They are plains made of hardened lava that erupted long ago. These volcanic eruptions left behind smooth flat areas called basalt plains. In the late 1800s, one sky watcher studied the Moon and found it didn't have an atmosphere. Without an atmosphere, there are no clouds and no air to keep water from evaporating. So scientists thought that any water on the Moon would just disappear right away. They believed the Moon was totally dry. But then, in 1961, one physicist had a different idea. He pointed out there could be water on the Moon in special areas called permanently shadowed regions. These are spots on the Moon where the sun doesn't shine, so they stay dark all the time. Water ice could exist in these dark areas because they're extremely cold and the ice wouldn't evaporate. But when astronauts from the Apollo missions went to the Moon, they brought back soil samples, and scientists found no signs of water in them. So everyone went back to thinking that the Moon was completely dry. In the 90s, NASA focused on these shadowed craters and found high concentrations of hydrogen, which meant there could be ice at the Moon's poles. They still weren't certain, so they kept digging and, after a while, found hydrogen trapped inside tiny beads of volcanic glass. Since there are no active volcanoes on the Moon today, which means water probably was present on the Moon when these volcanoes erupted long ago. Plus, there could be way more water back in the early days of our Moon. In 2020, NASA's SOFIA mission showed us what we'd been looking for a really long time. There is water on the Moon after all. It turns out the water is hidden within the grains of lunar dust or sticking to the surface in the sunlit areas of the Moon. So there are no oceans like we have on Earth, but at least there's something. The question remains, how did water even get there? It seems the moon had a chaotic history back at the time when it was forming, as probably most of the planets and moons in our solar system. So there is some evidence that water came there from comets hitting its surface back in the old days, or maybe even keeps on coming from those that are slamming into the moon right now. We're talking about a chaotic situation where icy micrometeorites collide with the moon's surface, and dust then makes an even bigger mess when interacting with the solar wind. But we're waiting to find out more about this. Because, as we all know, when you mention water, you also inevitably talk about life. That's why we want to know more, for instance, about all that ice hidden in polar craters on the moon. Maybe it can teach us more about how life developed on Earth. Maybe comets brought all the necessary elements here. Then, what if there are some of those elements stuck in the ice on the moon, too? Soaring temperatures of more than 11,000 degrees Fahrenheit, solid rocks of blazing superhot fire, immense pressures 3.5 million times stronger than on the surface of the Earth. These are just some of the things cooking 1,800 miles beneath your feet as you're watching this video. How? The sun is burning with a temperature similar to our planet's core, but it's 93 million miles away. So why isn't Earth melting away from its own core? Our little blue planet is made of many layers stacked one upon another. The inner core, the outer one, the mantle, and the crust. The deeper you go, the hotter and more pressurized it gets. Plate tectonics are layers of the mantle and crust piggyback riding, forever moving and just having a good time. Scientists discovered there are 9 plates in total in different parts of the world. When these plates move and grind on each other, earthquakes occur. Energy is released as a result, and we feel it on the surface. Think of it as trying to shut a car door after stuffing it to the brim. When you realize there's something in the way, remove it, and boom, everything topples. Billions of years ago, our lands were all interlocked in what was called Pangaea. But slowly, and I mean slowly, over the years, the continents drifted apart into what we have right now. The Earth was also cooler on the inside, but it slowly started generating more heat in the core. Earthquakes are measured with intensity and magnitude. We see how far the effects of an earthquake reach through magnitude, and the intensity is the measure of its power. Over at the mantle, the cooler rocks begin sinking and hot material from the core rises up. When this happens, the plates begin moving, and as a result, they create mountains, hills, and bodies of water we have today. None of these things happen overnight. It takes millions of years to actually see something. All the way in the layers of the Earth, there are different sources of heat, mainly from when the planet was initially formed. Friction heating occurs when materials begin sinking down to the center of the Earth. Since the Earth is surrounded by a solid mantle, the crust floating on top of it acts as a barrier to protect us from the Earth's insides. But the secret for its success is the difference between heat and temperature. Simply put, heat is just energy, and temperature is its density. If the sun was 1,800 miles away from the surface of the Earth and boiling at the same temperature as our core, we would melt like ice cream on a hot sunny day. A shock from a small short circuit when plugging out your phone charger from the socket won't be too harmful, even though a spark can have temperatures of around 2,700 degrees. But if you dipped your body in a boiling bath of hot water at around 200 degrees, let's just say it's not worth it. Just because the temperature of the sun's surface is roughly the same as the Earth's core, doesn't mean the heat distribution is the same. The Earth's core is teeming with iron throughout the layers, but on the surface, the iron atoms are arranged into cube shapes. That's when iron is in normal room temperature and regular pressure. But put in extreme conditions, the atomic shape changes into hexagons. For a long time, scientists thought that the iron in the core was hexagon-shaped, but they found out it retained its cubic formation 1,800 miles underground. Since the core has so much pressure, the atoms simply don't have a place to move to change their shape. If you were standing in a subway train that was packed full, you wouldn't even have space to lift your arm. But everyone inside is able to switch positions while keeping the original shape. That's why the structure of the Earth's core is solid and not liquid. The atoms are so tightly packed that they can't even transition into a liquid state. But in a world where the Earth's core are liquefied, we'd witness the worst consequences, starting with major and mass volcanic eruptions, earthquakes, and tidal waves. Every major hotspot would be in danger, and the Ring of Fire would be a non-stop fountain of lava spewing out. Cool material from the upper layers sinks down to the core and vice versa. With a liquid and incredibly unstable core, this process would be much faster. Every major city and town by the coast would be washed away by tidal waves, and all the volcanoes erupting will blacken the sky with ash and smoke. This would temporarily block the sunlight from entering our atmosphere and eventually force anything flying in the air to remain on the ground. The lands we currently live on would feel like ice breaking away from a glacier and floating off. Many dormant volcanoes would wake up from their slumber and spew out their morning lava all over the place. The ground formation and structure would change permanently. Magma from the bottom of the ocean trenches would find its way up to the surface and change the currents in the oceans. The Arctic Ocean and Antarctica would melt away and add to the rise of water levels all around the northern and southern hemispheres, and eventually the world. Wildlife on land wouldn't be able to flourish, and all the greenery would disappear. Marine life would have to find a way to escape the changes in the ocean temperature. The world economy would crash as an international emergency would be declared to try and figure out a way to stop this. But humanity would barely make it alive and would have to strive to continue existing. Well, of course, something like this will never happen. But if the Earth's core cooled down, then we wouldn't have massive volcanic eruptions, no devastating earthquakes nor tidal waves. In fact, none of these things would happen since they require energy to function. The continents would stop moving and changing. Sounds cool, right? No. This means that the magnetic field protecting our planet would disappear, which would make us extremely vulnerable to cosmic radiation, as well as asteroids and meteorites. The sun's rays will feel even more intense than usual, which will make it extremely unsafe for anyone to go outside. The heat produced in the core is responsible for recycling the carbon that goes back to the surface. Now, recycling would stop altogether. Carbon is an essential part of carbon dioxide that plants need to survive. So all the trees and plants on the surface and in the water would stop growing and wouldn't be able to produce oxygen for the rest of the world. With cosmic radiation and lack of oxygen, humans would have to live in bunkers with artificial ventilation systems. The Earth's surface would become a no-go zone and start to resemble Mars. With nothing to power the Earth from the inside, it'd begin to dry up and crumble internally. Much of the Earth's surface is made out of oxygen, so without it, we would eventually see something like major sinkholes around the world. Sinkholes that can take down cities like New York and Paris, along with landslides in many cities and unstable landscapes all over the place. Every single city's infrastructure would eventually collapse and make the ground unwalkable. So even if you did live in an underground bunker, chances are the foundation wouldn't last and you'd be exposed to the cosmic radiation. But all of this can vanish in the blink of an eye if an asteroid comes falling down. Whether it's tiny or colossal, we would be seeing more of those than actual rain. Without a magnetic field, the Earth can't block any foreign object that flies through our atmosphere. If an asteroid the size of Rhode Island came falling down, the damage would be much more than with the Earth's core hot and running. With the ground as fragile as potato chips, the ripple effect would be much wider and cause more indirect destruction around us. The Earth would eventually collapse in on itself and break into pieces until it's lost its own gravitational energy. It'd end up being a bunch of rocks and pebbles floating around in the emptiness of space. But nothing like that will happen either. We're living fine with our solid hot Earth core. As long as it's doing okay, then we can keep on doing our thing.
Hey, I want to show you something. Let's take a little trip off of Earth and park our spacecraft somewhere near the moon. We're now almost 240,000 miles away from our home planet. That's almost 100 times the width of the United States. Now we've brought a special set of tools with us, a giant hammer and an enormous chisel. Place the chisel at the Earth's North Pole and strike its head with the hammer. The Earth cracks open like an eggshell and we see Another planet? This is Theia, and it's hiding inside our planet like a yolk in an egg. If you want to find out how it got there, you'd need to travel back in time 4.5 billion years. This beautiful nebula is what will eventually become our solar system. Colored dust and various space debris are slowly coming closer toward the common center. Over time, this jigsaw puzzle of debris becomes denser and heavier. The temperature inside the giant is rising. Soon, it gets so high that it'll trigger a nuclear chain reaction. One more second, and bam! There's an explosion so powerful that the shockwaves travel far into deep space. When the dust clears a little, you can see that a bright light is still shining at the very center of the explosion. This newborn star is the Sun. It weighs as much as 333,000 Earths. If the Sun was a bucket, you'd need 1.3 million Earth-sized planets to fill it. But we're interested in that small object over there, 93 million miles away from the Sun. This pile of rocks and hot lava is Earth. Right now, the planet is busy forming its core while the oceans of lava are gradually cooling down. But some millions of years later, after the Sun's birth, you notice another small object. Here comes Theia. This small planet was formed at about the same time as Earth, and right now, it's following a crazy spiral trajectory at enormous speed. Scientists believe Theia was like a ball Jupiter and Venus played around with. Venus would pull Theia in one direction, and then Jupiter would pull it right back. But what makes up 99.8% of the mass of the solar system is the Sun. It's what makes Theia move into almost the same orbit as Earth. So they inevitably come closer and closer to each other until they become next-door neighbors. We see that Theia is roughly the size of Mars, as wide as the Atlantic Ocean from New York to Portugal. At this point, the collision can't be avoided. Theia is traveling towards Earth at nearly 9,000 miles per hour. That's 11 times faster than the speed of sound. If this smaller planet would crash into Earth at a particular angle, Earth would most likely be torn apart, as well as Theia itself. The collision would cause a huge blast visible on other planets, even on a bright day. Nothing would be left but some burning dust and debris. Even if Theia only slightly grazes the Earth, it'll still knock out a sizable chunk. But the collision with Theia happens at a perfect 45-degree angle. It strikes the Earth at tremendous speed. The explosion literally vaporizes huge amounts of rock, and the shockwave sends the remaining debris into Earth's orbit. A huge crater is formed at the impact site, which soon gets filled in with boiling lava. The remnants of Theia and the ejected fragments of Earth begin to orbit our planet. According to one theory, these fragments actually form two moons. At first, they travel together, but one day they get too close to each other and collide, forming one large space body. The other theory claims that all the loose shards get pulled in by the remnants of Theia, and that sometime after that, they form the moon, as we know it today. At this point in the past, though, it's just red-hot rock and lava. The collision at this angle slightly tilts our planet and accelerates its rotation. It's because of Theia that we have different seasons and 24 hours in a day. Now, Earth also has these things called lithospheric plates. These are enormous solid land masses that make up the crust of our planet. After the collision with Theia, they start to break and crack. It causes carbon, a primary component of all known life on Earth, to start moving all over our planet, so Earth gains a kind of metabolism. After a few 100 million years, the first living creatures start to appear on our planet. Over the next nearly 4 billion years, simple single-cell organisms evolve into the kinds of complex life you see today. According to scientists, a collision like we had with Theia is a very rare event. The probability that somewhere out there there's a planet like ours that has survived the same catastrophe is even rarer still. This may be the reason why we have yet to find other traces of other civilizations out there in space. Meanwhile, the remains of Theia are still here on Earth. Of course, it doesn't look like an actual entire planet stuck inside our own. Most of the fragments have melted and blended into the Earth's crust. If you take the top layer off our planet, you'll see two huge lava blobs the size of large continents. They're right below Africa and the Pacific Ocean. Presumably, these are the remains of Theia. They didn't mix with the Earth's mantle because of different densities. It's like mixing water and oil in a glass. The oil will always float up over the water and create an even layer on top of it. But if you raise these lava patches up to the surface, they'd be 100 times higher than Mount Everest. Other remains of Theia might be on the moon. The Apollo space missions brought back many soil samples for analysis, which led scientists to conclude that the moon is very similar to the Earth in structure. Someday in the future, people could drill deep down and take samples of the moon's crust. Then they'd analyze the blobs from Earth, and if their structure matched, it would be undeniable proof that Theia did hit Earth 4.5 billion years ago and gave us the moon. But for the time being, Theia remains an unsolved mystery. Scientists are still not sure that the planet actually existed. The whole idea does perfectly fit the model of the moon's creation, but it's also possible that this incredible collision may have never happened. Now, let's travel 41 light years away from Earth to the planet 55 Cancri e. It's about twice the size of Earth and 8 times heavier. Let's take out our giant hammer again and use it to hit the chisel. The planet cracks, and you see it's a giant diamond. The temperature on this planet is tens of times higher than on Earth, and its soil is rich in carbon. The heat puts a lot of pressure on this carbon, and the structure changes. First, it turns into graphite, but then add just a bit more pressure, and the graphite turns to diamond. On Earth, diamonds form at depths 60 miles below sea level, where the pressure is 50,000 times greater than that on the surface. And the temperature there averages over 1,000 degrees, which is as hot as fire. Diamonds are often ejected closer to the surface in volcanic eruptions, but still, people mostly have to dig mines 1,500 feet deep to find these beautiful gems. Currently, the Golden Jubilee diamond is the biggest cut and faceted diamond on Earth. It weighs as much as a chocolate bar and is the size of a hamster. Its price is about $12 million. Now, imagine a diamond the size of an entire planet! Now, let's fly back to our solar system. Our destination now is Jupiter's moon, Europa. It's as wide as the distance between Seattle and Houston, and its mass is less than 1% of the mass of Earth. Its surface is enclosed in an icy crust that's about 19 miles thick. Europa is completely covered in water. It's freezing here, 3 times colder than that of the North Pole and Earth. The water turns to ice almost instantly. But the ocean beneath the surface is still liquid. Europa has a gravitational relationship with Jupiter, just like the moon with the Earth. This creates tidal forces that heat Europa's core, which then melts the ice around it. The result is a huge ocean, 2 or 3 times larger than that of Earth's oceans combined. Scientists believe that water is one of the essential ingredients for life. This means that life may exist on Europa. There could be thermal springs, just like at the bottom of our oceans, though the water there is probably much warmer. And even though the pressure and temperature in such places are likely to be extreme, simple bacteria could live there. Europa is almost the same age as Earth, so there has been enough time for living organisms to appear and evolve. Who knows? Maybe some advanced civilization is already blooming under this crust of ice. They might be building big cities and dreaming of conquering space. But for now, all we can do is speculate. And maybe someday send a probe to Europa to find out if life is possible there.
Now, let's pretend that humanity faces a huge threat from outer space. So we'll imagine that a giant planet-eating octopus comes to our solar system to eat Venus, Mars, Earth, Jupiter, and other planets, except Saturn. Therefore, people decide to move to the big planet with giant rings. Fortunately, they already have cool technologies that allow them to make such trips. So we get into giant ships, take off, and fly to Saturn. Life on the planet itself is impossible because it has no solid ground. The ship won't be able to land there. This is a giant gas ball that is 9 times wider than Earth. To compare their sizes, look at a 5-cent coin and a baseball. And the planet's atmosphere consists mainly of hydrogen and helium. So if the ship starts to land, it'll never reach solid ground. And the lower it goes, the higher the pressure it will experience. Eventually, the ship will just be crushed. Therefore, we have only one choice: the rings of Saturn. They're made up of giant, medium-sized, and tiny particles of ice and rock flying around the gas giant at tremendous speed. They were formed from comets flying by. Saturn's gravity knocked these celestial bodies off their course and crushed them with its pressure. Fragments of these comets began to accumulate around Saturn, forming rings. Now, some of these particles fly faster, some are slower. The closest to the planet is the D ring. It's followed by rings C and B. Then there's a large gap called Cassini division. Rings A, F, G, and E come after. This classification is very convenient for creating a ring map. So, people approach the rings, but don't dare to land on them. First, they send test capsules with robots to scout the area. The robots choose a suitable location on the E ring. In fact, the distance between the rocks is quite large, and the ship can easily fly there. There are tiny particles, huge rocks the size of houses, and comets the size of a whole mountain. The first robot flies up to a large rock at high speed. At this moment, a baseball-sized stone pierces the robot's body. Another robot gets smashed between two colliding boulders. The third robot gets caught in a rain of sharp icicles and breaks. People have big engineering workshops on their ships, so they build new capsules and new robots. This time, they're made of more durable materials, so the robots reach a big rock again. A few particles crash into them, but don't break through the armor. The machine set up a small station on a flying rock where people can live. But after a couple of hours, a big chunk of asteroid smashes the station. Well, seems like we need another strategy. Giant ships scan the entire area of the E-ring and calculate the trajectories of billions of stones. After lengthy calculations, people finally find the perfect places in the middle of this chaos that will stay intact for a long time. They land on these large rocks in their capsules and begin to settle down. They build stations and small houses and install powerful batteries on them. Saturn is located at a distance of 9.5 astronomical units from the Sun. 1 unit is the distance from the Sun to Earth. So, Saturn is a pretty cold place. That's why there's so much ice flying around it. But how to get the energy to heat it all up? There's too little of it on large ships. Besides, solar panels are ineffective here because of the great distance from the Sun. Therefore, scientists create a way to generate kinetic energy from flying stones. It's like a windmill. When the wind drives the fans, these movements are converted into energy. So engineers build panels that collect power from the moving stones. But it doesn't slow the speed of rocks down because Saturn's gravity continues to move them. Thus, people receive a source of almost limitless energy. Some space stations have plants and trees that produce oxygen through photosynthesis. Only instead of sunlight, they get energy from ultraviolet. Then, people fill large tanks with oxygen and carry them to their homes. People begin to occupy the adjacent rings. You don't need a lot of fuel to get from one place to another. You can land on a rock, calculate its route, and wait for it to bring you to the needed point. Then you can move to another one, and so on until you reach your destination. More and more people leave their ships and move to the rings. It seems that life is getting better, but then psychological problems begin. Constant movement in the vacuum of space drives everyone mad. Imagine living on a carousel that never stops. You can't walk to the store whenever you want because it always flies away. No one can go out for a walk, even in a spacesuit, because there's a chance to come across a rock flying at high speed. You can't plan anything because, at the moment, your plans can be ruined by a giant piece of ice. Computers don't help either. They can't calculate the trajectories of all space bodies. Rocks tend to break and split into hundreds of smaller ones. Also, new comets fly by and also become part of the rings. All this creates uncertainty and causes a sense of anxiety in people. Besides, it's dark, cold, and very lonely on the rings. Now think about building a base on a space object, but your best friend lands on another one a few miles away. Then, a giant icicle crashes into his rock and increases its speed. And a few days later, your friend is too far away. And it happens all the time. The only way to change your life is to settle on one of Saturn's moons. The planet has 83 of them. People have already confirmed and named 63, and the existence of 20 others has yet to be confirmed. They're all like different worlds. Some of them may be habitable, and the best candidate among them is Titan. There may be water on it, and its atmospheric pressure is only 1.5 times greater than Earth's. Its atmosphere consists of nitrogen and a little methane, forming carbon smog in Titan's upper layers. For this reason, we can't study this moon from Earth. But the coolest thing is that Titan flies outside the rings of Saturn. This means people can lead a quiet life there. There's also satellite Phoebe, covered with craters like our moon. This giant celestial body looks more like a gigantic meteorite. People have a lot of choices of where to start a new life. During a couple of 100 years spent on ships near Saturn, humanity would learn everything about its satellites. But why did they try to live on the rings? Why didn't they land on one of the moons from the very beginning? Because, well, then this video would be less fun and a whole lot shorter. But what if we were initially born inside the rings of Saturn? Let's say a massive meteorite with frozen water got caught by the planet's gravity. There were the simplest life forms inside the ice, and then this life began to acquire more developed forms. Imagine that the large rock managed to remain untouched for hundreds of millions of years, and during this time, humans appeared. But of course, they would be very different there. Firstly, they wouldn't experience gravitational forces. This would make them taller, but weaker. People's skin would be pale because of the lack of light, but very hardy thanks to cold temperatures. Particles of ice and grains of sand flying in space would roughen people's skin. In such biological armor, without gravity, they would jump from one rock to another in search of food and water. And, by the way, that would be the main problem. How would people survive without oxygen in the vacuum of space? Where would they get their food? Saturn's rings are a pretty lifeless and dangerous place. If there are not even the simplest forms of life there, then how could such a complex one as the human appear? Therefore, even in theory, the appearance of people would be impossible there.